you can start.
Okay, thank you very much. You are welcome back to this training. So today I'm going to quickly give you an overview of this course, which is the design of a water distribution system using an Epanet. And I think my colleague Uche will take you the real case study and the computer application. So today we are going to take the step-by-step process that if you are called as a consultant, if you are called as an engineer to come and design a centralized water distribution system for an estate or for a school or for a community, what are the steps you need to take? And what are the information you need at that particular point in time so that you should be able to come up with all the data collection you need before you can move into the proper design. The first step is what we call site visit and survey information. When you are called as a consultant to come and design a water distribution network or water reticulation network system for a community, for an estate, the first thing you need to do is to visit the site, to visit the community. Where is this reticulation system need to be carried out? Why do you need to go to those places? One is to get the topographical map of the area. What do you need the map for? To get maybe the digital elevation model so that you should be able to get the spot heights and the elevations of that area. So when you should be able to also know the total area to be captured, and you should be able to know the contours. Probably the surveyor will give you all those informations. You may follow the surveyor to the site, or you might not even go, but the surveyor will provide all this information for you. You will know the digital elevation model, the DM. You will know the elevation of the land. You will know the total land size. You know the contours so that you will be able to know their different spot heights. When you get that, you will come up with a map like this. This is like an example of a digital elevation model. You can come up with a map like this. So tomorrow, next tomorrow, when Uche will be teaching you the computer application, you will see how Uche can upload a map like this, digitize the network, and come up with a real network system. And at the end of the day, he will hide this map. You will only be seeing the network you need. And there is a way if this map is actually where you reference, if you position it into the software, the actual length you measure from this map on the software will actually be the actual length on the ground. So you will learn more about that on Saturday. So after getting this information here, you will move to the next step. The next step is what we call the housing density and population projection. That is the next step. What comes here is, what type of housing are you going to build? Is it terrace? Is it semi-detached? Is it duplex? Is it bungalow? How many units of those buildings do you need? Do you have in that estate? Is it even an existing building, or is it a new one? Is it an existing one that even need an expansion? When you get all this information, you have to come and calculate the population. When you know the numbers of housing that are available in the estate, for example, 10 numbers of building, assuming this time all are bungalow. Conventionally, there's supposed to be, let's say, 5 people per housing unit. That is the normal standard, 5 people per housing unit. But maybe in the case of Nigeria, we can have more than that because we have a lot of family. You have a brother, you have a sister, in-law will come in and other. So, but when you get the population currently of the area where you want to design your water distribution system, the question is that population going to be stagnant throughout the design period? Is the population, has it been constant since that community has been in existence? In that case, you have to determine the population variability of that estate or of that community, because there is birth rate, there is death rate, and there is migration. And some people even also live, either immigration or as migration, the people live. When you get that, you will be able to determine the current population of that area, probably from population census, which is normally conducted every 10 years. But when you have that, you can't just use that because their population is going to vary during the design span of the water distribution system. In such a way, in such a case, you have to determine or forecast the future population as against your design periods. There are 3 methods popularly used in forecasting population as against your design period. The first one is the arithmetical progression. This method is used for old cities. If you are called to come and design a water distribution for an existing community, this formula is used. This formula assumes that the rate of growth has been constant over the period. In such a case, if you are going to project, assume we are here this year and now, and we want to project into 10 years' time, what you will do, this formula will now give you population in 10 years' time is equals to the current population plus this constant rate of increase times the population for the design period, which is 10 years. If the constant rate is 4%, is for you to multiply 4, you multiply 4 by 10 and add it to the current population we have now. In such a case, you will get the population you are forecasting against the 10 years period. 2, please, let me check that noise. Where is that noise coming from? Okay. Can you hear me? So now I
can hear you. Go ahead.
Mr. Sunday, Engineer Sunday is muted, please.
Mute
myself. Okay. Can you hear me?
Yes.
Okay. The second method is the geometric progression, which is used for new cities and younger cities. If you are just newly constructing a community or an estate, you use the geometric progression. The reason being that the geometric progression gives you a higher value when you compare it with the arithmetic progression. If you look at the formula critically, this is the formula that is used to calculate compound interest in economic analysis. When you have the present worth of amount and you have the numbers of years, you have the interest rate. So in this case, this is the growth rate, which is the arrow. The N is the numbers of year, YP is the present population. This is a form of a sticky fund. If you have done economic analysis, the value seems to be higher as compared to arithmetical progression. In that case, it is used for new city because there is tendency that there is going to be a geometric progression where you newly create city, people are trying to quickly come into that cities. So we use that formula to calculate the population progression, and where the value of our arrow can be estimated from this formula, which Uche will be talking about during the case study tomorrow. The other one is incremental increase. At times, you will have population that is decreasing and increasing. In such a case, you will have a negative growth rate. As a result of that, you use this formula, incremental increase. This formula gives you a value that falls in between the arithmetical progression and the geometric progression. So in that case, you will use this formula to calculate the population forecast for that community as against your design period. Now, the first step is to go to site visit and get your survey information. The second stage is housing density and population projection. After your population projection, what next do you need to do?
Hello, sir.
Hello.
Can I quickly ask a question?
Yeah.
My name is Lukman.
Okay.
Looking at the population projection for new site, new city.
Yes.
How are you going to determine the PO, the current population, since it's a new site, there is no one there? So
yes.
What value are you going to use for you for PO?
You will use the community around, a nearest community. or probably the population census that is going on within that state. Because that is why it's called in a decade.
Also, you can also use the land use. If you know the land use of that area,
yes,
it will also give you an idea. The land use is the density, like you said, the density per hectare. Normally, when cities are planned based on high density, medium density, high density. Low density can be like, say, 200 people per hectare. Medium density can be like, say, 500 per hectare. 1,000, high density can be 1,000 per hectare. So it depends on the urban and regional plan of that city. Thank you.
Okay. The third step. Now, the first is survey information and site visit. The second stage is population projection and housing density. The third stage is localization and water demand. Now, based on your population, how many people do we have in that community? How many people are going to be living in a particular housing unit? Based on our population forecast, assuming the total population we have in that estate is now 100. That is the numbers of people living in that estate. That is called the capital. Now, what is the water demand? There are different tables and standards for calculating water demand. For old buildings, you can use about 113 liters per capita per day. Then for new city, you can use about 115 liters per capita per day. If one person is consuming 115 liters per capita per day, and you have 100 people in that estate, so the total water demand is going to be 115 times 100. That will be the total water demand. Now, when you have that total water demand, you will go further to estimate what we call the daily water demand and the hourly water demand. In a pipe distribution system, if you are taking water from the borehole, from the water source to the elevation tank, the pipe that you use is what we call the transmission pipe. If you are the pipe you are taking to take water from the overhead tank to the consumer house is what we call the distribution type. Now, the transmission pipes and the distribution pipe, they are not supposed to be the same diameter. The distribution pipe will be higher and the transmission pipe will be higher than the distribution pipe. That is the only way you can always have water in the reservoir. But if they are the same, a point will come that the tank will be empty. In such a case, you have to calculate what we call the daily water demand and the hourly water demand. The daily water demand is used to size your transmission pipe, while the hourly water demand is used to size your distribution pipe. And these are formula for them, which Uche will not be talking about tomorrow. And we also have factors we can use to multiply them to get our daily water demand and our hourly water demand. During your case study tomorrow, we will be talking about that. Now, the first step is site visit and survey information. The second step is housing density and population projection. The third step is localization and water demand. Now, the fourth step is now localization and the pressure zoning. This is where you will pay more attention. At this point, sometimes I asked one consultant one time, the consultant said in an estate, they have two overhead tanks. One is at 12 meter high, the other one is at 8 meter high. I asked a question. I said, why do you decide to use two overhead tanks? Why not one? So the response was, this is how we have been doing it. Oh, is that really correct? So something moves you, something tells you whether you are going to use two overhead tank or one overhead tank. You don't just come in and begin to construct only one tank. That is the point we want to discuss here, which is the localization and determination of pressure zoning. Now, the pressure zone indicates the necessary elevation of the overhead tank for each portion of the system so that every consumer we receive a water at a good service pressure. In a residential building or in a municipal water distribution system, the minimum service pressure for a floor is 20-meter water column, which is equivalent to 2 bar. 1 bar is equivalent to 10-meter water column. Why sometimes pressures is being related to meter water column is that pressures is sometimes related with elevation. And elevation is in meter. If we are taking pressure in a bar, we can add the two together. But when you convert it to meter water column, you can easily add them together. That is why we normally use 20 meter water column in water distribution system. So 1 bar is equivalent to 10-meter water column. So the minimum service pressure available for a floor in the municipal water distribution system is 20-meter water column, which is 20 bar, and the maximum is 18-meter water column. Otherwise, you should be talking about water tower. Now, the service pressure available to each consumer is a function of the numbers of floors in each building, the age of the distribution, the altitude difference between the distribution network, the elevation storage tank, and the numbers of buildings in the distribution system. Now, I will want to show you something. Now, let me go to this one. Now, how can you zone your area to know the numbers of overhead tank you will have in that estate? The numbers of overhead tank you need is equals to the numbers of pressure zone you have in that estate. To calculate the numbers of pressure zoning you have in your estate, the first thing you need to do is to get the map, which we already have during the first stage, which is site visit and survey information, that your digital elevation model with contour lines. In that case, you have to determine what we call the upper limit of housing, which is the maximum elevation in that area. 2, you have to determine your lowest limit of housing, which is the minimum elevation in that area. When you have that, the difference between the upper limit of housing and the lowest limit of housing will give you what we call the elevation difference. Now, I said earlier, the minimum service pressure available for a floor in a residential building is 20-meter water column. If you have 2 floors, what you need to do is to keep on adding 5 to each floor. If, assuming I have 2 floors, it will not be 25. If I have 3 floors, it will not be 30. If I have 4 floors, it will not be 35. You keep on like that until you get to the maximum service pressure, which is 80. Now, when you get that elevation difference, the difference between the upper limit of housing and the lowest limit of housing, the next thing is you calculate the height of zone of the estate. The height of zone is given by this formula, which is SP maximum minus SP minimum minus the depth of your reservoir tank you are proposing. You will know that beforehand. Either is 4 meters or is 5 meters. And you will calculate your frictional head loss, HF. In a consumer tap, in the municipal water distribution, the frictional head loss is 10-meter water column. After that, you will calculate the numbers of zones. Now, let me go and show you what we mean by this in Excel sheet. I will show you another Excel sheet now. Can you see my Excel sheet?
Yes, we can see it.
Okay, now let me come up with so that you will be able to know how many zones you have in your estate. Now, we have an estate. We have an estate. The building there, the highest building there is 3 floors. If we have 3 floors in a building, what is the minimum service pressure? Who can tell me now? From what you said just now, the minimum is 20. When you are increasing in the floor, you add 5. What will be the value now?
35.
35.
35.
Is it 35?
Yes, 35.
One floor is 20.
Yes.
Two
So
floor
that's
will be
30.
25. Three floor will be
30.
13. That is 13.
Yes. It's
30.
Okay, it will be 30 meter water column. Okay, that is fine. Now, in this estate we have, when we take the survey map, we discover that the highest elevation in that estate is 240 meters above sea level, which is the elevation. That is the difference between elevation and height. So the upper limit of housing is 240 meters above sea level in that area. That is what we call upper limit of housing. The lowest elevation in that estate is 185 meters, which is what we call the lowest level, the lower limit of housing. Now, when we take the difference between the upper limit of housing and the lower limit of housing, it's going to be 240 minus 155, 185, which will give us what? 55. When we have this 55, when we just now, the formula I show you is when you get the elevation difference, the next thing you need to do is to calculate the height of zone. The height of zone just now is the SP maximum, which is 80 meter water column, the minus SP minimum, which is the 30 we just determined just now for 3 floors, minus 5, which is the tank height assumed, and minus 10, which is the frictional head loss in the pipe as 1 bar in the municipal water distribution. That will give you 10 meter water column. You can see why we convert the bar to 10, because we can easily subtract the bar away from elevation. So when you get that, you are going to have 35. The next thing you need to do is to compare this elevation difference, 55, and this height of zone, which is 35. What you need to do is to divide to get the numbers of zones you need in that estate, is to divide this 55 by this 35. If I divide this 55 by this 35, I'm having 1.6. 1.6, a zone cannot be a half. I will just adopt 2. What that one means is that in that estate, I'm going to have 2 pressure zones. I'm going to have 2 overhead tanks. One will be at zone 1, and the other one will be at zone 2. That is the way you can calculate the numbers of overhead tank you have in an estate. Now, what happens? This is the zone. This is the complete area. This is the zone 1. This is the zone 2. Now, the minimum elevation, the minimum lowest limit of housing is 185. The upper limit of housing is 240. When we subtract this, we have this 55. Now, what you do is that zone 1 will be equals to this height of zone. First of all, the height of zone is 35. You first of all bring out the full 35 to make one zone. That is the zone 1 we have, and the height of zone is 35. The zone 2 will not be the remaining one to make up this 55. If I subtract this 35 away from 55, I will have this 20. So if I add this 20 plus this 35, I'm having 55, which is the elevation difference. So zone 1 will be within a range of height of zone of 35 meters, while the zone 2 will be within a height of 20 meters. But the next question that will now come in is that, what if we now want to, after getting this information, the next thing is, if we want to put the tank, what will be the height of the tank in each of the zone? Like what that former consultant did. It has a 12 meter high, the other one at 8 meter. I said, how do you know it's 12 meter? How do you know it's 8 meter? He said, this is how we have been doing it. So now you need to know the height of your station in zone 1 and the height of your station in zone 2. In that case, you will come up with this. let's say this is the height. Just let me scroll up. Let's say this is the tank in zone 1. This is the base. Then this is the stanchion. In zone 1, if I come down again to the graph, if I come to this graph again, if I come to zone 1, the lowest, what is the lowest limit of housing in zone 1? Who can tell me to know if we are following?
185.
185. What is the upper limit of housing in zone 1?
220.
Okay, good. 220, which is 35 plus this 185. Now, what is the lowest limit of housing in zone 2?
240.
20.
Okay, there the upper limit of housing will be 240. Okay, good. Now, when we now come to know the height at which we are going to put our tank, this is zone 1. This is the height, this is the stanchion normal base. Then the lowest limit of housing we have is, we take it from the lowest level, which is the elevation different from here to here. This is the lowest level of the tank. Now, the lowest limit of housing elevation is 185. Now, what you will do when you get this 185, you will come up with this formula here. This formula to help you calculate your lowest level, the minimum level of your tank, which is the estimated lowest feed level of the tank, which is here now, is for you to get your upper limit of housing. Upper limit of housing in zone 1 is 220. 220. And the HF, as we normally use, is 10. And the SP minimum is 13 for 3 floor. So when you put, this is 220 here, this is 10, this is 13, and you are looking for this, then the value for this will be 220 plus 14, which will give you 260. That means, what that one means is that, this level here, this point here, is at 216 meters in elevation. And your lowest level of lowest limit of housing is here at elevation. What you do, you subtract this 216 away from this 185. You will have 75. That 75 is the maximum elevation difference where you can put your tank in zone 1. What that one means, it doesn't mean that you are just going to, your stanchion height is just going to be 75 meters. No. What it means is that you can come here. If 75 is our case, you will come here. If this, you can move, you will now move around your estate. Where can I locate? Where is the good soil where I can easily locate my stanchion? If you bring your stanchion to this point, let's say 200, it means that your lowest limit of housing is not 200. It's no longer 185. The higher you move up, in the elevation to put your tank, the shorter will be the height of your stanchion. This one means noise. Okay. Now, what that one means is that you can play around any of the attitude here and put your tank. But what to the upper limit of housing, the shorter will be the height of your stanchion. But the worst case scenario is to put it here when no other area is available in the estate. So in that case, the lower you go, the more you go closer to the lowest limit of housing, the higher will be the height of your stanchion and the more expensive it is. Now, when you finish that, you quickly get the total height of your upper limit of fee is to add this 216 plus the height of the tank, which is 5 meters, you get your upper feed level. You apply the same method to this ZO2. ZO2, the lowest level will now be 220. The upper one, using that same formula, you will get to about 280. So what that one means is that if you check the difference is 16, it doesn't mean that the height should be 60 meters. What it means is that you can play around here. You can play around between here and here. The closer you are to the upper limit of housing, the shorter will be your stanchion and the more economical it will become. So this is how you can calculate your pressure zoning in your estate to know the numbers of zone you have and the height at which you are going to put your stanchion. It's not just an eye guess. It's not just that I have done it somewhere before, it's going to work here for me. So at this point, I will go back to my Excel sheet. We have discussed 4 stages now. We have discussed 4 stages, which is the first one is the site visit and survey information. Stage 2 is the house density and population projection. Stage 3 is localization and water demand estimation. 4 is localization and pressure zoning. So when you are through with that pressure zoning, then the next thing, maybe you go evaluate the water quality, which we'll talk about tomorrow. Then these are water quality. The next thing I will quickly talk about now is pump. And hello, yes.
Can we ask question?
Yeah, you
Yes,
can raise
go
your
ahead.
hand next time. Yeah. Go ahead.
Okay, sorry. Yeah. Please, can you go back to the formula, please?
In the Excel sheet.
The formula
Okay.
The formula H zone SP max
Minus SP minimum.
XP minimum.
Minus height of tank.
Yes, so I want to know more clarity on this the data H reservoir and the HF.
This data H reservoir is the height of your tank, of your overhead tank, which you can assume before design. You can say, okay, it's 4 or it's 5. Then this
height of the overhead tank.
Yes.
Yeah, like the bottom and the top.
Yes, the difference.
The bottom, the difference, that difference is what the lowest water level and highest water level.
Yes.
So it's not the stanchion height, but the height, let's say the height is a 2-meter tank or 4-meter tank.
Yes.
Okay.
Yes.
What about the HF?
So the HF is the frictional head loss. Now, it's constant value in the consumer tap for a municipal water distribution. The maximum head loss there is 1 bar. That 1 bar is equivalent to 10-meter water column. That is why you just use 10-meter water column. You can see all these things we are relating all these things, the pressure and the elevation. That is why you can see that a pressure zone, the bar is being converted to meter water column. 1 bar is equivalent to 10-meter water column. So it's about.
Yeah, the 10-meter is it a rule of thumb estimate?
Yes, for a municipal water distribution, at the consumer tap is 1 bar.
There must be a basis for that. I'm trying to understand.
It's like a design code. When you have a design code where you pick values, so there's no need of you deriving it. So people have derived it and they come up with it.
It's an assumption. Let me just also chip in. It's an assumption.
Yes.
In design. They are standard you assume. So we assume that the network, 1 bar is reserved for bends, taps, and losses.
A conventional, yes.
Somebody raising hands. Who is that, please? Okay. Okay, still a rabble. You can put down your hand, please. If you still have another question. Go ahead, please.
Okay. Now, the next one I will quickly talk about before.
Sorry, I'm raising up my hand. Sorry.
Okay. Sorry. Go ahead, sir.
Sorry, can you probably shed more light on the upper limit and the lower limit?
Okay.
I think I follow others. I didn't actually get that aspect of it.
Okay. Assuming this is a map, assuming this is your topographical map,
Mhm.
where you have contour lines.
Mhm.
When you have contour lines, you are going to have the highest elevation in the estate.
Above the sea level.
Yes, that highest elevation is what we call the upper limit of housing.
Okay.
The lowest one is what we call the lower limit of housing.
Okay. Clear. Thank you.
Okay. Now, let's go quickly to, now, in the centralized water distribution system, there are components that make up the distribution network, which is the water source, a borehole, which is the tank.
Okay. Hello, sir.
Reservoir. Yeah.
Please, how did you get the 20 and 35 in the zone 2 and zone 1, sir?
20 and 25 in the Excel sheet.
And 35. Yes, sir, in the Excel sheet.
Okay, let me flag the Excel sheet quickly. Can you see the Excel sheet?
No, not yes, sir.
Okay, now you know how we get the upper limit of housing, which is 24. We get from the map. The
Yes,
lowest limit of housing is 185. This
Yes.
limit of housing and lowest limit of housing, which is this 55, correct?
Yes, sir.
Now,
Yes, sir.
you know how we get this height of zone, which is the SP maximum minus SP minimum minus HF minus elevation difference. The formula we just showed just now.
Yes, sir.
Okay, fine. When we get this, then we get this 35. Now, this 55, to get the numbers of zone, you divide this 55 by this 35. When you do that division, you are going to have 1.6. So a zone cannot be half. You just adopt 2.
Yes, sir.
When you now adopt 2, this one will be zone 1, this one will be zone 2.
Yes,
Now,
sir.
what you will do, the zone 1 will first of all take the whole full pressure. This is the whole full pressure we have for the height of zone.
Okay,
This zone
sir.
1 first of all take this full height of zone, which is 35.
Yes,
so
sir.
the remaining one, which is 35 minus 55, 20, is this 20.
Okay, sir. Okay, thank you, sir.
Is it correct? Are you okay now?
Yes, sir. Thank you, sir.
Okay, fine. So we have two more people hands.
Robert, can you say something?
Yeah.
Yes, sorry for hanging on this point with this Excel, but the height of the tower. First of all, when we talk of height, I guess we talk about the height at the outlet of the tower. When the water...
Of the tank.
Yeah, from the tank.
Yes.
So, and then should it not the height of the outlet of the tower should be 20 meters higher of one tower for zone 2 and one tower for zone 2, meaning the outlet height of the tank should be at 260, respectively at 240, isn't it? Or do I get it wrong?
Yes.
And then I look basically for a point in my area where my tower my tower is not 10 meter high or not 20 meter high, only like 6 meter or as low as economical as possible, basically. But the outlet of the tank should be 2 bar above the upper limit of each zone, or isn't it?
Now,
yes.
Say what we are saying now. When you have this is the tank. Let me put something here.
Yeah.
This is the inlet. This is the inlet tank. This is the inlet tank. And let me say this is the outlet. Now, what we calculated as the upper feed level is this tank, the lowest level of this tank here. Just consider the tank. Then the upper one is this. But in a deep tank situation, we have what we call a buffer that will not allow the tank to be filled to the brim. Now, in Epanet, yes, the freeboard, yes. On Saturday, when you will be using Epanet to size your tank, you will see Epanet will require this value from you from here to this place. and take note of the freeboard. Epanet will also ask you about this minimal water level here. And Epanet will also require the initial water level in the tank. You know, the water in this tank can never go below a certain point, so that there will be some water remaining here, which you can use to flush the tank. So all those values are required. So what you are asking now is that at this point, this is what we call the upper feed level, which is the 216 we calculated. This 216, this 216 is here.
Yeah.
Why
the
height of the tank is 5 meters, the upper one will be 6 meters. But when you are distributing in the distributed water network, when you move it from here, is 2 bars, you said. But at consumer tap, that is where you expect the losses. That is where you expect the losses at the consumer tap. That is where the head loss there is 1 bar, which is equivalent to 10-meter water column. But here is 2 bar at the tank. But at that 2 bar is not a function of the sizing of the height of the tank. It's a function of the pipe that is going away from the tank, which is the distribution type. So by tomorrow, when Uche will be talking about distribution pipe, which is the pipe taking water from the tank, and the transmission pipe, which is the one taking water from the reservoir to the tank, Uche will talk more about that one tomorrow. Is it okay now? Okay, so let me quickly go ahead and finish the other one. Now, the one I was discussing just now is this water distribution system has various components. One, you have to know the source of your water well, either a borehole or from a lake, or you have the storage tank or the reservoir. You can have the pipe, you can have the pumps, you can have the overhead tank and the valve. Uche will talk more about this one tomorrow during case study and also during the computer application. But there is one information I want to quickly get here. You have been hearing about the concept of borehole drilling. People are saying a deep well and shallow well. Who can actually tell me the difference between the two? Because many people have been having misconception about that, and I want to clear it here also. Who can actually tell me the difference between the deep well and the shallow well?
Well, I think it might depend on the area. Deep, shallow well, there are deep boreholes that are not deep, probably to like say between 20 to 50 meters, whereas deep well goes from like 150 down to about 250 meters into the ground.
Okay, now let me come up with something like this. Just excuse me. Oh, Joseph. Oh. Yeah, you are around. I'm in the class. Now, let me show you an example here so that we clear that doubt. Can you see my screen? Can you see my screen?
Yes, we can see your screen.
Yes,
the
we can
element of
see your
centralized
screen.
water supply system.
Okay, just let me open door for someone. Sorry.
While we are waiting for Engineer Sunday, the question Robert asked also, I think the 240 is
Okay.
this
Now, let me say something. If you have, let me put this concept to explain it. If we have, this is a well, this is a borehole, and this borehole is the water elevation in this tank is, let me say, is somewhere here. And we have another borehole. And let me say, this one, you see, we go like this. We have this, and the water level in the tank.
We are not seeing. Oh.
Okay, you are not seeing my screen.
I'm seeing, but the indicator is not moving.
Really? Okay, let me reshare again.
The pointer, yes.
Can you see it now?
Yes, yes,
Mhm.
yes.
Okay. Now,
Yes.
let me use the that concept. Okay, what I'm trying to say, okay, let me just put the label. I'll just put the figure. If this borehole, if this is a borehole A, if this borehole A is, let me say, is 10 meters, and the water level in the tank, and the water level in this tank is 3 meters, and this tank is 12 meters, and the water level in this tank is 2 meters, and this is borehole B. If a man of 3.5 meters high should fall inside this borehole, which one will kill the person? This borehole is 10 meters deep, and the water level in the tank is 3 meters. This borehole is 12 meters deep. The water level in the borehole is 2 meters. If a man of 3.5 meters, if a man of 2.5 meters should fall inside these two wells, which of the well will kill the person?
It's A.
The one that is 3 meters deep.
The one that is 3 meters deep will kill the person.
Yes.
Because the person is 2.5 meters high, it will be buried here. Why the person will not be buried in this one?
Yes.
So you can see, despite that this borehole is deeper and this one is shallower, then if two people fall into the well, this one will kill the person. What that one means is that the depth of borehole drilling is not a function of the depth of drilling. It's a function of the water volume of water inside that porous medium. So it's not a function of the depth of drilling. That is why you can have an aquifer that is unconfined, but the volumetric rate of the volume of water in the aquifer will be very high. We also have a deep confined aquifer, but the water is shallow. So the volume of water is a function of whether a borehole is deep or not. So I quickly cleared that concept. So let me go to the last point of my presentation for today. And now, when we get this component, we collect the water, we transport, we treat, we store, and we distribute. Now, the most important things I want to show to you is this. The concept of pump quickly. Because of sometimes when the water network, when the tank is at a higher elevation than the pump, than the water source, water cannot flow by gravity and go up there. As a result, what you need to do is to use pump to move the water to the tank. Now, the main function of the pump, okay, this gravity flow and this pump flow. Now, the main function of the pump is to raise the water head, the pressure head in the system so that the water will be able to. But one big problem of calculating the rate pump head, the pump, the formula for pump is this. The rating of pump is the manometric head divided by the Q, multiplied by the Q and the acceleration due to gravity divided by the efficiency. Everything is a kilowatts. What that one means is that the rating of a pump is a function of two parameters, which is the pump head and the flow rate. But the issue of calculating the pump head is a big problem to many people. And when you are using the Epanet next tomorrow, if you fail to give the accurate head to the software will shut down the network. It will tell you that water cannot be delivered to that point. So in that case, I will show you how to calculate the pump head. Now, when you have two reservoirs, two tanks, there is a tank here, there is a tank here. But because this tank is at a higher elevation, you need the pump to boost the water, to raise the pressure head of the water so that you should be able to get water in this tank. So what we first of all do is to get the elevation difference between the two tanks. Tank is at this elevation, the tank is at this elevation. The difference in the water level in the tank. We have the water level here, we have the water level here. The difference between the water level between the two tanks is called the geodetic head. That, or you can also call it an elevation, but it's the geodetic head. You will note it down. Now, by the nature of water flowing in the system, there is what we call the frictional loss, which is the pressure loss. That pressure loss, when you draw a line that move towards like this and go here, we are going to have this pressure head here. This pressure head is P divided by rho G. Is P divided by rho G. That's where you get this pressure head. Now, this pressure head, this line you draw is what we call the hydraulic grid line. It's what we call the hydraulic grid line. As a result of pump be present in the system, there is another loss that will be induced as a result of the pump. And that will create another head that is called the energy grid line. Maybe we call the another line called the energy grid line. This energy grid line is as a result of the introduction of the pump and is parallel to this hydraulic grid line. Now, the difference between this hydraulic grid line and this energy grid line is what we call this value here, which is called the velocity head. That is as a result of the introduction of the pump in the system. What it means is that we have the geodetic head, which is the elevation difference. We have the pressure head, which is P divided by rho G, and we have the velocity head, which is V squared divided by 2G. Now, to get the full pump head is a summation of the geodetic head plus the pressure head plus the velocity head. And because the velocity head, this pressure head plus this hydraulic grid geodetic head is what we call the manometric head. But all the three sum up, we give you the total head. But in calculating pump head, you neglect the effect of the velocity head because it tends to be negligible. Because if you take a velocity of flow in a water distribution to be, let's say, 0.6 meter per second, and you square it, which is V squared divided by 2G. If you square 0.6, it's going to become about 0.036 or so. And if you multiply it by, if you divide it by 2G, which is 2 times 9.81, you can see the value will be 30 towards 0. So that is why in calculating your pump head, you just neglect the effect of the velocity head. Then you use the manometric head, which is a summation of the pressure head and the geodetic head and the pressure head. So when you get that, what you now do is, why do you need all this? Is to know the size of your pump. When you come to this, you use this formula. This formula, this 1000 is here because the flow rate is in liter per second. But when the flow rate is in cubic meter per second, this 1000 will automatically disappear. Then when you calculate this pump, the capacity of this pump using this formula, you are having to, you get the answer in kilowatts. Then you can easily convert from kilowatt to horsepower because 1 horsepower is equivalent to 0.746 kilowatts. Using that, you can easily know the rating of your pump and recommend to your client, you are going to buy 2 horsepower pump, 1 horsepower pump. Then another effect, another thing we'll quickly discuss in pump is what happens when you, for example, you recommend to a client that the pump, the capacity of the pump needed to pump that water is 2 horsepower. But on getting to the market, 2 horsepower pump is not available in the market. It is only 1 horsepower pump that is available. Then you decided to buy 2 numbers of that horsepower 1 horsepower to give you that 2 horsepower in combination. As an engineer, how will you arrange those 2 pumps on site so that you will be able to get the required head or the required flow rate? In other words, when you are arranging 2 similar pumps in series, how does it affect the head of the pump? How does it affect the flow rate of the pump? So when 2 similar pumps are being arranged in series, the flow rate will remain constant, while the head will be double. When 2 similar pumps are being arranged in parallel, the head remains constant, while the flow rate doubles. So when you fall into that situation on site, you should be able to know whether you are going to arrange those pumps in series or you are going to arrange those pumps in parallel. Now, the last phase I will not discuss is now, a pump, the efficiency of a pump is always less than 100% because of the energy needed to overcome the friction in the pipes. Now, how do you determine the efficiency of your pump? When you buy a pump in the market, normally you have what we call the characteristic pump curve that will follow the pump. We also have the efficiency curve. In Epanet, in the software, when you will be using it tomorrow in sizing your pump, it will require you to give the pump curve. What is a pump curve? A pump curve is a curve of flow against head. When you plot a graph of flow against head, you are having a pump curve. But we also have what we call the pipe curve, system curve. When you plot a graph of flow against the length of the pipe, you also have what we call the pipe curve. Now, what you do to calculate the efficiency of your pump, what you do is when you get the pump curve, look at when you plot a graph of Q against H, you are having a curve of this nature. This curve is what we call the pump curve. When you plot a graph of Q as against the length of a pipe, you also have what we call the pipe curve, something like this. The curve will look like this. The point where the 2 curves meet is what we call the operational point. Then you also have what we call efficiency curve. Efficiency curve is a curve of efficiency against flow rate. When you get the efficiency curve, you place it under this pump curve. Now, what you will do, the pump curve, the efficiency curve will also look like this. If a curve of efficiency as against the flow. All those curves will be available in the software next tomorrow. So what you will do is, when you get the operational point here, where the 2 pump curve and the pipe curve meets, what you will do is to trace it down. You will not trace it down. Where it meets up with this curve, you will not trace it to this side. The value you will have here is the efficiency. In this case, it's about 60% efficiency. So that is the efficiency you are going to put, that is the efficiency you are going to add here in this formula. That is the efficiency you are going to add here in this formula. So now, having done that, the last point I'm going to discuss now is your tank. How do you determine the volume of water in your tank? Ideally, most consultants design their overhead tank, they over-design their overhead tank. Remember today, I said to get the water demand in your estate is to get the total numbers of population and probably multiply it by about 130 to 150 liter per capita per day for one person. You will get the total water demand. The question is that total water demand, is that what you are going to use to size your overhead tank? If it is 50 cubic meter, are you just going to design your tank to meet up with that 15 cubic meter? No. If you do that, you are over designing your tank. What you need to do is what we call equalization volume. You will calculate what we call equalization volume. That the actual volume of your overhead tank is equalization volume plus volume for emergency plus volume for firefighting if you are not separating the volume for firefighting separately. If you are separating the volume for firefighting, you just combine the volume for equalization volume and volume for emergency. And how do you get the equalization volume? Why is it not important? Now, if human being, the way we consume water every day is not the same, it's not constant. But the rate at which the pump move water from the water source to the overhead tank through the transmission pipe is constant. And as a result, if you take it cumulatively, you are going to have a straight line graph. But the way we consume water in the morning is not the way we consume water in the afternoon. It's not the way we consume water in the evening. As a result of that, we have what we call consumption pattern. In the Epanet software next tomorrow, Uche will be telling you how to create a pattern to show the way you are consuming water. So when you create that pattern, you are not going to have a straight line curve. The curve is said to be an S curve when you take it cumulatively. Now, this is how the curve will look like. This is a curve of the consumption pattern. In the morning, for example, in the morning when people are going to school, the demand for water will be very high. Around 9, the water demand will be low because people are not in school, people are in the office. As from 2, 3 coming home, the demand will be high again. That is the consumption pattern we are talking about. Now, if you not do it in such a way, you will not have, if you the transmission, that is the inflow, the way, the rate at which the water is going into the tank is the inflow rate. So that inflow rate cumulatively is going to be a straight line curve. But the way people are not consuming, which is the distribution pipe, in other words, this is a curve of, the blue one is a curve of the transmission line, and this curve is a curve of the distribution one. I told you earlier that you will use a daily water demand to size your transmission pipe, and we use hourly demand to size your distribution pipe. When you plot the graph like this, you will now look for the maximum difference. If you want to check it, is here we have the maximum difference. The maximum difference between the inflow rate, which is this blue line, and this outflow rate, which is this green line, is what we call the equalization volume. When you get that volume and add the volume for emergency, that is the volume you are going to use to size your tank. If you use the actual volume from the water demand you calculated, you are going to be oversizing your tank, and it will not be economical. So that is how you calculate your equalization volume. And at this point, I think the presentation for today, this investment cost. So those who will be interested in this, maybe they attend the cost engineering session. That is where we normally discuss everything about cost, how you do cost estimating and all of that. But as a concept, if you are called as a consultant to come and design a water distribution, 1, site visit and survey information. 2, house density and population projection. 3, localization and water demand estimation. 4, localization and pressure zoning. That will help you to know the numbers of zone you have, the numbers of overhead tank you have, the height at which you are going to put those tanks. And from there, you do your pumping system, you do your piping system. If you are using valve, you can include your valve and all those components. These are the general fundamental principles of designing a water distribution systems. And maybe later, Uche will take you to some of the advanced case study. Tomorrow, he will enter properly into the real case study, and on Saturday, he will give you the computer application. So at this point, I will end my presentation. I will say equal to the first break. And if you have questions before, maybe we go to 5 minutes break, you can ask the question. Thank you very much.
Thank you so much.
Thank you, Engineer Sunday. So we've come to the half of the class for today. I would like to entertain questions. After that, we'll observe a 5 minutes break. Maybe you can take water or something, or you can still hang around just for 5 minutes. So if you have any question, we would like to hear from you. If you have a different perspective from what Engineer Sunday have said, you can as well air your views. If there's no question, we're going to do a 5. Okay, two people are raising their hand. Irabo and Gideon, David, can we hear you, please?
Sorry, my own is about the materials. I've not gotten the materials.
Okay. You have my yeah. WhatsApp. Can you chat? Gideon, have you been to a training before?
No.
This is your first time?
Yes.
Okay. Okay, please. And you've paid, I guess.
No, I'm yet to pay.
Okay, maybe that's why. Why is that why you're yet to get the material?
Okay.
So maybe after the class, just chat me up later.
Okay.
Thank you very much.
Thank you.
All right. So any other question? What Engineer Sunday have done is to lay a foundation. You know, it's good for us to understand some of these terms, like pump in parallel, pump in series, pump curve. How do you know your service pressure? And from your bottom of your tank, that's where you take the reference from. Then how do you size your transmission pipe? Is sized daily, based on daily parameters. Why the distribution pipe is sized based on hourly parameters. And many other things he said. And I think in the next class, in the next section, I will just be giving us I will present a small case study for us. Then from tomorrow, we'll go into the design proper. So any question? Should we go for a 5 minutes break, or do you want us to continue? Can I get your opinion? Okay, Robert, your hand is still raised. I don't know why
yes.
Okay.
We go on break.
Okay.
I have a question.
After this question, okay.
Hello, please.
Well, for the tank volume, you said, okay, we should read out from this graph, we should read out basically the maximum difference between basically a linear inflow and basically the curvy outflow. But how do we read this? I mean, the reading of this graph, how do you do it? Like vertically or I mean, how can I read the graph before that? This one.
Okay.
So I don't know if how to read, you know what I mean? Like how to read, how to get from this graph now I see this area where there's the maximum difference, but I still wouldn't know how to read it in cubic meter.
Okay, okay, no problem. So let me explain it to you now. Now, you know the water in the day we consume water for 24 hours. That is the 24-hour
green line
from 0 to 24 hours. Now these other ones are the volume for the first hours. You pump up, for example, we have what we call the pattern step. That pattern step, you can break it down into, say, 4 hours. From 0 to 4 hours. That is how Epanet will do it for you tomorrow. You create a 6 pattern step. Okay, from 0 to 4 hours. Yeah. Let's the demand and the flow rate be the same. Then,
but where did you read the 50 cubic meter?
Yes, I'm coming.
Show him how to read it.
Yes, I'm coming first. Let me show you how you get the line and get line and take the difference. Now,
Yeah, I get
at
I
these
get
4
this one.
hours, you get the cumulative inflow and you get, okay, fine. Now, what we do, when you come here now, if you look at this graph generally, where do you have the maximum difference? Should be somewhere here.
Yes.
If I take straight like this. So if you take a straight like this between, if you are taking, let's say 8 as a point, and you have, okay, you take the inflow here and you trace it up straight to meet up with another line here. The value you will meet at the inflow here, and the value you will meet at this outflow here. When you take the difference, that is where you get this 50. For example,
Okay, so okay, I get so I go like basically vertically, and then I go to the left, and then I do the readings. Which because the 50 I cannot, if I go from what I instinctively out of the belly, you know, where you have the 30, I would go up. I would go up vertically, and then I would probably get something between this 25 and 75 cubic meter. Then it's the 50.
Yes.
Okay. All right. Thanks.
Okay. Okay.
Yeah. Hello.
Go ahead.
Yeah.
You have like 3 minutes. Yeah.
Okay. I just want to, the philosophy of this graph. From my understanding now of this graph, you are saying that you need, if you need a 200, if the daily demand was 200 cubic meter, then the number of the actual storage to be stored is about 50 cubic meter. Am I correct?
Yes.
Okay. Going by this interpretation of this graph, you are saying that the transmission line, the pump has to work for 24 hours. Am I correct?
Yes.
Yes.
Okay. So that's another perspective to the design. The way we our own perspective is that this transmission line, the pump is not expected to work for 24 hours to fill the tank.
Go ahead, sir. Go ahead. We're listening.
So what we normally do is for our overhead tank, that's how we normally use a daily storage, or we use maybe half daily storage. Then for the incising the transmission line, that is the supply line to the pump, we can estimate like 1 or 2 hours for the operating time for the pump to work, meaning that in 2 hours your pump can work in 2 hours to fill the required daily volume of water that is required. So your pump doesn't have to work 24 hours at every instance. So your pump will just work when it will work maybe like 2 hours or 3 hours a day, then it stops. So that's our own philosophy.
Now, the philosophies are the same. It doesn't change. What you people are doing, you people assume and calculate. So have you ever think of is it not possible that at a point that tank will be dried? Now, the ideal situation is that we have what we call, as I said earlier, what we call the daily water demand. When we say daily water demand, the volume of daily demand is higher than the value of hourly demand. What that one means is that while the pump is pumping at a daily rate at a higher value, the way the water is leaving the tank is at a lower value, which is the distribution pipe. So that hourly demand is used to size distribution pipe, while the daily demand is used to size transmission pipe. Now, what we do is that, what if you are pumping this water, what can you do? If you are pumping this water for 24 hours, what is the value you can get? That value you can get is what you people are using factor to do. I say, okay, instead of pumping for 24 hours, but why can't us pump for 8 hours and leave the other one? But you must have done it for 24 hours. That is the pumping rate. You must have done it for 24 hours to really know the flow rate, the actual flow rate at which that tank is filling up. So, but to not get to actually relate, because consumers are demanding water 24 hours. If consumers are demanding water for 24 hours and the inflow is now at maybe 8 hours, you can say we cannot relate the actual computation together. In other words, we can also stop at 8 hours for the outflow. But what happened to the remaining hours? To really get the comprehension nature of the two graphs, they must be at the same level. It doesn't mean the pump must be pumped 24 hours. That is why if you look at this graph, if you look at, let me, which of them? I'm coming, let me show you this. Pumping. Okay, you can see where we say it must be made simple and flexible, e.g. like 8 hours pumping. You can pump for 24 hours, but for you to get the situation report, and even in the software itself, the software, they know this, they also calibrate their auto to 24 hours. So it means that you have to do that to get the technical idea of what you are getting. But if you stop pumping at a point, don't you know that your tank is going down at every point? Your tank will also be going down at every point. So what we are trying to do in order to save costs, that is why we are not pumping 24 hours. But that doesn't mean we should not use it to estimate the actual volume of water we'll be expecting in the tank, which is called the equalization value. Otherwise, if we design that your own, it might even be over designing the tank. Everything is to avoid excessive cost. Some consultant will just design and multiply by 2. That is over design. So you have to calculate the equalization value because of the consumption pattern and not take the maximum difference. That will not be the volume of your tank when you add the water for emergency. But the way you are doing it doesn't mean it's wrong, because you have already just tried to factor in a value to size it. But at every point in time, distribution line is equal to your distribution line. The tank might be empty at a point. Thank you very much.
Thank you.
Okay, thank you. Also, okay, so let me just also draw his attention to other content of this material. If you look at this material, this is an 8 hours pumping. Engineer, who asked that question again? So these are 8 hours. Okay, these are Shitu. Okay, good. This is for 8 hours pumping. So it's not like you pump for 24 hours. If I go further, you see for 16 hours pumping. Okay, this is 24 hours you saw, and this is 8 hours pumping. So you can see that the pump started at 0, let's say midnight, and at 8 hours it stopped, and consumption continues. So just like your Sunday said, whether you pump for 4 hours or you pump for 24 hours is the same thing, but sometimes it's good for you to know the maximum and the minimum of the tank sizes you are meant to provide. And the good of the thing is that you answer the question right. The size of tank to be provided is the difference. The highest difference, like the highest difference here is 200 minus 30 for 8 hours pumping. It means I'm providing a tank of 170 cubic meter. Whereas if you go further, for 16 hours pumping, for another 8 hours pumping, but pumping between 8 and 4 o'clock and 16 o'clock, you're going to have a smaller tank of 100. If you now move further, you get another size. So it does depend on the maximum and the minimum inflow. So if you are using a shorter period, you're going to get a bigger pump size. If you are pumping for a longer period, your tank size will be small. If you are pumping for a shorter time, your tank size will be bigger. So
it makes sense.
If you're pumping for 2 hours, it means you're going to provide, like, let's say, a bigger tank that will sustain you for the next 22 hours. If you're pumping for 4 hours, it means you're going to pump probably the tank size that will take you for the next 16 hours. Whereas if you are pumping, let's say in between, if you program it very well and you pump in between 8 hours in between the day, it will come to, let's say, half of what you have. So I think if you go through the material, you know more about this. Okay, Engineer Sunday. Okay, thank you.
Hello.
Yeah. So let's just, I think we should resume at this point. So just like what Engineer Sunday said, we have done a good job in giving us the overview. What I just want to do is to present in a very quickly, before I introduce our case study, is to introduce us to a PowerPoint, which I presented many years ago for the Nigerian Institution of Water Engineers, which I know that Engineer Sunday relates to it. Just a summary of what he has just said here. Engineer Sunday made us understand that if you have to be doing a design, just a recap of what he said, you need your map, your description of the area, you need your calculation basis, where he talked about expected growth, where he talked about the future development. And then after that, you now talk about the calculation of water demand, which has to do with, which he said is about 130, depending on whether you are the population density of the area. Then it is after you have done all these things that you now go to your distribution network, your analysis, and then your conclusion. So what I will be doing now is I'll be laying a foundation for what we're going to do for tomorrow. So here we have in your manual, this is what you have in your manual. Those that have downloaded the manual. You have the Epanet software in your first folder. Then the second folder is your images and materials. So just like you said, before you do your water reticulation design, you need a base map or a topographical map. You need a base map, you need a layout or a topographical map. So here we have included some layouts of Google Map and georeference map, which you can use to practice. Then the third material here is your lecture materials. Now, these lecture materials will lay a foundation for some of these things he has been mentioning, pressure zones, water demand, and what have you. So here in these 8 chapters, you will have the opportunity of learning every one of them. So what you need to do is after this class, I'm going to take the next 1 hour and go and brush through everything here. And I expect us that between now and tomorrow, some of us will have to go through it. So after going through it, you can now come back for tomorrow before we start our case study and then ask your questions. Then after this, yeah.
Have you shared these documents?
I have shared it to all the participants. Maybe who will speak in place?
My name is Lukman from CA Consultants.
I think I've shared with some of your people. Yes, yes. So now the next material you have.
Hello,
yes,
sir.
Sir. Mm-hmm.
You haven't received the material. No.
Nobody actually from my office. That's another person from my office.
I'm sure I shared it to Lupe and Hamid. I'm sure. Check your chat. Some of us don't look at our chat. It's in your chat. Look at the chat. Yes. Okay, let's continue. But if you've not gotten it, don't worry, you'll get it, please. Don't worry yourself.
Okay.
Good. So the next material you have is the pressure zone, which so this is a Excel sheet to understand your pressure zoning.
Somebody want to ask a question, so I think.
Okay.
Or is I think a robot want to, because I'm saying the hand up, or has it been up?
It's been up, Robert.
Okay.
You need to take down your hand. Okay.
Okay.
Then the next thing you have is what I call the workshop files and data. If you open this, you have about 12 information there. Now, let me say this. Part of what me and Sunday have been doing, we have been trying to downscale this knowledge. And what we've done is to gather every possible material you can lay your hands on that can help you in doing a proper water system reticulation. Now, the first file there is a case study we're going to treat tomorrow. The second file is a case study you can practice on your own. The third file is an exercise we're going to do on Saturday. The fourth one is the second exercise we will do on Saturday. The fifth one is the Epanet manual. The Epanet manual will introduce you to the software proper. And mind you, the software is an open source software. So you can go to epa.gov and you download it. And if you want to know and become a master in it, we have included the manual for you. So there you can, it's not something you can learn in 3 days. So after the class, you can continue and become an Epanet guru. Okay, this is not necessary. This one too is not necessary. This is a case study of a map in Germany we used. That is necessary. Then the next one you have is what we call the nomogram. We have 3 charts. For every pipe sizing you want to do, you need what we call a nomogram. A nomogram is a chart which you can use to size your pipe after you've known the flow. With the flow, the roughness of the material, and the slope, you can size any pipe. The most important input parameter to size a pipe is your flow. Then your slope will also be important because the slope will be able to help you determine the velocity at every point. And we all know that the velocity is very important because there's a minimum value expected in the velocity in the network, and there's a maximum value. Just like in your Sunday mentioned that in a network, the minimum pressure is about 2 bars or 20 meter cube of water. And the maximum is about 8 bars, which is equivalent to 80 cubic meter of water. Why do we have this minimum and pressure? Because we need to be guided by code and standard. For instance, for the pressure standard, if your pressure is more than 8, you have to zone them. If you don't zone them, the material we have in the market, some of them cannot take more than 8 bars. So that means there's going to be pipe burst. Even if the pipe, you are going to buy new pipes. There are modern pipes now that are up to 12 and 16 bars. But we know that the average pipe in the market, as at 2-3 years ago, is about 8 bars. And even if you can buy a bigger pipe bars, how about the appurtenances? How about the other component of the network? Can they sustain any bar, any pressure that is more than 8 bars? So that is why you do that. For the velocity, the minimum acceptable velocity of flow in your network is about 0.3 meter per second. And the maximum is about 3 meter per second. So it's a factor of 10. Why do we say this? Because we want your water in your network to, if pressure is too low, let's say in the case of a C1 network, you're going to have deposition. It means that the water will not flow accordingly, and that could lead to siltation of the network. Okay, then if the pressure, if the velocity is so high, and that could lead to supercritical flow. And when you have this supercritical flow, it could lead to crustation of the pipe. That pipe will not last long because you'll be hearing noise, there will be corrosion. There will be erosion and corrosion of the pipe. So in this material that we are giving you, we have included 3 different charts, depending on the roughness factor. As I said again, there are 3 factors you need to size your pipe: the flow, the velocity, the slope, the flow, the slope, and then the pipe roughness or the frictional factor. So if you are using, let's say, a PVC pipe, you're going to use the monogram for 0.1. If you are using a pipe like ductile iron, you use the second chart of 0.4. If you are using concrete pipe or asbestos pipe, which has been banned, you're going to use a nomogram of 1.0. So this is what the chart looks like. Let me just open one of them. By tomorrow, we'll use them, or at least we'll learn how to use them. So this is what the chart looks like. In every pipe sizing, you need a chart. Some of you that attended the lecture, the training last week on sewer and stormwater, you will agree with me that we also make use of this chart and one other chart again. So for everything in pipe sizing, is either use a table or use a chart. And some of us that are civil engineering background, you know that is either use a chart or use a table. We normally use chart or table. Both of them go hand in hand. You can downscale this chart into a table. It will give you the same thing. And then when you don't find your value, you can easily interpolate. So for this chart is the vertical axis is a meter cube per second. You can see it here. And the horizontal axis, sorry, is a meter cube per second or liter per second, which is the same thing. Liter per second and meter cube per second are the same. It's just a factor of 1,000. And on the vertical, you have the slope. So with the slope, we all know how to read chart. We're all engineers. If you give me a chart to read, once I get the value for the vertical, I'll read it correspondingly to the value at the horizontal. And whenever it stops, that is where I will read off my value. In the case of this chart, it's just like psychometric chart. Two parameters will give you two parameters out. For instance, let me just give you an instance. For instance, let's assuming that my flow, my Q is 10 meters per second. After I've done the population equivalent, the water safety factor, and all those parameters that we listed earlier today, I will now read off this chart. And let's say that the slope is, let's say 2%. I'll read my chart against 2%. So it will fall in between here. So once I get in between here, it means that this chart is falling between two pipe size. And those pipe size are 150 millimeter and 200 millimeters. So it means that the flow at this point can either take a 150 mm pipe or a 2 mm pipe. But the advice is for you to take the biggest one, because in engineering, we design based on worst case scenario. So let's leave it for now, because tomorrow we're going to come to it. So back to what you have in your material folder. The next thing you have is what we call planning design case study. So that's what we're going to look into. We included this to give you an idea of how your report should be like. So if you go through this report, you see the standard reporting template for a water distribution design. After you have done your design, you are expected to present it in form of a report, a consultant report. So we have thought it wise to include a template for you here, so that when all you need to do is to convert this into Word document and format it and then use it. So this is what your report is expected to be like. Number one, it will have a title, a case study designed for Victoria Island, you name it. You name the number of the people that are involved in the consultant, or you just name the name of the consulting company that did it. After that, you have your table of contents. After your table of content, and your table of content will be in those 5 chapters that Engineer Sunday just enumerated. You do your introduction, you do your description, your scenario, your expected development, your water demand for firefighters, your water losses, your water demand, your calculation in projection after you projected your number of years. Then you talk about the working steps in your chapter 2. You talk about the description of the steps in your chapter 3. You now go to computer application. So I'm not going to go through all these because the material is at your disposal now. So you can go through it at the end of the day, or whenever you do your design, you can fall back on it and it will guide you on how to prepare your report. This is not cast on stone. It's just a template to give you a perspective of how we did it ourselves. It does not mean you do exactly what we did, but it will help to form the skeleton of your work. Okay, the next thing in your folder is a PowerPoint presentation, which Sunday have gone through already. It has gone through. It will just show you the step-by-step approach that you're going to use in a PowerPoint format to do your design. You know, why this is important for us is that, you know, most times how to do a design is always the same thing. It's just the same thing, your introduction, the site analysis, the catchment characterization, You talk about your demand, you estimate your demand, then you generate your factors, and then it's just a simple step-by-step approach, which every design engineer is already used to. The next folder is your drinking water requirement. He mentioned it again. Okay, in selecting your water source, there are criteria that you use to select your drinking water source, because the quality of your raw water determines the treatment process you will adopt. We have, let me open it. We have surface water, we have groundwater, we have spring water, we have rainwater, and so on and so forth. So this table will also give you an idea of the quality limits of the treatment you're going to apply. Okay, after treating your water, what are the limiting factors you need to realize? For instance, we have the microbial, the biological parameters, we have the chemical parameters, and then we have the physical parameters. Okay, so all of them have limiting factor, and those limiting factors are, we have the German standard, we have the European standard, and we have the World Health Organization standard. So these standards will guide you. For instance, let me just draw one attention to us. In drinking water standard, there should not be any biological parameters. That's why you see 0. For E. coli, it should be 0. For coliform, it should be 0. Then from fungi, don't mind the language, this is a German word, intercocken, is just mean other water organisms like fungi and the rest of them, which are undefined. So in other words, for a drinking water at the tap of a consumer, there should be no trace of biological elements, whether it is coliform, whether it is the E. coli or other bacteria and fungi, there should be no element of them. But then when you come to something like fluoride, we expect your fluoride to have a limit. It shouldn't be too much, it shouldn't be too less. So we expect it to have an upper limit of 1.5. Anything less is good, but 0 is not acceptable, because some of these chemical parameters are beneficial to the human body. Okay, and if you look at something like nitrite, nitrite has a limiting factor for 0.5 on German standard, 0.5 for European standard, and then the World Health Organization was a little bit, it's been a little bit flexible between 0.2 and 3.0. So these are all the material you have in your folder. So why I did this is for you to know how rich, that beyond the 3 hours we're going to spend today, tomorrow, and the next tomorrow, you have much more to fall back on and be able to learn more. Okay. Then here you have, normally in our physical training, you are meant to register. The form is there, but no need for that because all of us have already registered via the Zoom. Then we have a service chart where you can see the losses based on the bend. I remember what my colleague said. He said, as a rule of thumb, you give 1 bar. We are in a municipal, remember? In other words, in a district design, you allow 1 bar to take care of losses. You allow 1 bar based on standards. Sometimes we don't meet those standards, but the fact that we don't meet those standards does not mean that we cannot understand that there are standards. Like when he talks about 2 bar, 20 cubic meter of water, the minimum. Yes, but sometimes you see people having like 1 bar in their network. Well, it would simply affect the quantity and the quality of the network, but that does not mean that water will not flow. But then for water to flow at a very effective, efficient, and standard flow rate, we expect the water pressure to be about 2.5, 2 to 2.5, but 2 is the minimum. And the maximum, as we have said, is 8. And optimally, it should be 3, between 2 and 3 in your network. Those in C and A, do you have a different perspective to this? Lukman, do you guys have something you use in your network? Is there any standard pressure? And what is that value?
That range is the acceptable limit.
2 to 3.
from 3 to 6.
Okay.
Yeah.
Well, the limit says 2 to 8, so you can play around. You can fix your safe value. For me, safe value is 2 to 3. For me,
And it is dependent on the faucets.
elevation.
Yeah.
Yeah.
It's also dependent
elevation.
on the. It's also dependent on the end use faucets.
Yeah, I understand.
Because if some faucets, some they require their high pressure demand high pressure fixtures.
Okay.
Maybe the operating pressure for maybe
like jacuzzi,
for a shower
jacuzzi.
might be 3 bar from manufacturer recommendation.
Yes.
So if you are using 2 bar, you won't get the optimal minimum requirement. So it's also based on the manufacturer recommendation.
Yeah.
So that's our guide.
But there's a caveat to that. While you are doing your design, you don't factor in individual comforts. You work based on cost and efficiency. Now, I agree with you, because what people do these days is that if the pressure in the network is so low, you can get a pressure boost and attach to that equipment. And again, one other thing you mentioned, which I like, is that it depends on the natural condition. You didn't say that. There are some conditions that are favorable to you to have a pressure that is up to 5 or 6. And there are some conditions that are flat land. So if you want to achieve such a big pressure, it means your elevated tank might be beyond your budget. Let me use that word. Okay. Then the next thing I included is some AutoCAD drawings, because in most cases, what you have to do as a consultant is that these drawings will be given to you in AutoCAD format. And once this drawing is given to you in AutoCAD format, it means you need to have a way of converting them into a picture format, because most of these open source softwares, they don't recognize DWG. DWG is default standard for AutoCAD. Rather, they depend on what we call bitmap images or image files. So sometimes you might do a little bit of conversion. So here I've included some AutoCAD drawing for us in 2007 and then higher version, so that what you do is when you open them, you convert them. So I'll be doing that on Saturday. If you give me an AutoCAD drawing, I'll have to convert it to a picture format, a JPEG or bitmap, and then import it and use it as a background to do my digitalization, just like we do in GIS, okay? In most spatial infrastructure work, there's always that need for you to digitalize and then come up with your own custom boundary or custom layout. So we'll be doing all that on Saturday. So that is all the material you have for this course. Remember, the physical cost of this course, the physical training cost 50,000 Naira, but for the online, we felt that there's no overhead, there's no too much logistics, there's no feeding. Even though there'll be certificates, we felt we should do it at 25,000 Naira, so that, but you're going to get the same full measure of what you would have gotten if it were a physical training. Believe me, you're going to get the same thing. There's nothing, no plus, no minus. And again, I want to encourage us engineers, and I want to also commend all of us that came for this training. The number is quite appreciable. I appreciate it. This is the new normal of learning. Today, I've had a lot of conferences online. The last 2 months, I've been having training with GIZ. It's absolutely via all virtual. And I think the more you have these trainings online, the more you get used to online training. And after a while, it becomes the new normal for you. Some of us might be feeling a little bit uneasy if this is our first time or second time. But believe me, as time goes on, we are going to be enjoying virtual training. You will find out that it's very, very good and it's very helpful, because you do it at the comfort of your home. You don't need to travel. You don't need to spend a lot of money. And you will get the recording. You get the same material, at a very cheap price. Okay. So the last thing also I want to also mention is that some of us saw the link and we logged in. It's not your fault, but there's a cost attached to this training, and that cost is 25,000 Naira. So please, if by adventure you've not paid, I want you to know that at the end of today, you are expected to make your payment based on the account number stated in the email and the SMS you got. So please, after the training, you can message me and then you effect your payment, because tomorrow, if I didn't see your payment, I'm afraid in order to give you the much needed value, we might have to put you in the waiting room. In fact, I've already put somebody in the waiting room this afternoon because he attended the last training and he's here, and I've not seen his name in the payment list. Please, so after this training, while the training is going on, you can as well chat me up. And okay, I don't have the DWG file. Engineer Aminchi Joshua, after the training, you're going to have it. Please, anything you don't have, you feel free, you're going to have it. We're not going to hold back anything. The software, you will install it after today, and we're good to go. So what I want to do now in the next 1 hour is what we did at the University of Stuttgart for 3 months. Yes, I'm going to collapse a 3 months coursework in 1 hour. Why I'm doing it is because I'll be skipping and I'll be jumping a lot of things. You see, I always tell engineers, when you come for trainings like this, what you need to do is to grasp the basics. If there's anything you need to read and understand, then it doesn't make point. It doesn't make any point somebody going through it. I don't believe in bringing slide and then reading slide for you and then explaining slide for you. No. So I would like to go to the basic now. So in the next 1 hour, I'm going to do a semester course for you. So I will start with chapter 1 and I'll go through them. Now, let me warn you ahead of time. Some of those content will be boring for some of you who are already water experts. But then, as I said, it's also good for you to learn somebody who already know it. So for chapter 1 now, let me open chapter 1. So as soon as I get to chapter 8, we're going to end the class. So chapter 1, what is so this is what I would have asked us. Of course, please, our materials are exclusive. If you want to use them, just let me know. What are your motivation? What are your expectation? I believe our motivation and expectation is for us to understand how to use a water reticulation system. But I don't know if somebody else have another motivation. If you have any motivation other than to learn something new, please put it in the chat box. Maybe you want to understand pump sizing, pipe sizing, reservoir sizing, or there's an exclusive something you are looking out for. Please, the chat box, you can put it down there, and I'll make sure that in the course of this training, I'll make a detour and explain that component for you in such a way that you derive home your value, which have made you to pay for this training. So for us, we have a general goal. And our goal is to understand the fundamental structure of a centralized water supply system or a centralized water reticulation system. And the number 1, 2 goal is for us to understand the hydraulic system, which my colleague just explained. You need to understand the hydraulic system, the basics. The number 3 goal is for you to understand the function and the structure of every single element. And then finally, we want you to get the ability to plan, design, and calculate for a centralized water supply system and each single element. So we all know water. Water can come in different form. Up here, you see somebody in a well. Then up down here is a glass of water. Down here is an intake structure in a reservoir. Now here you have a reservoir. This should be an underground reservoir. When we say reservoir, your reservoir can be underground, it can be surface, it can be elevated. On your right, you have a pumping station. You know, when you have more than 1 pump in a place, that place becomes a pumping station. You can call it a pumping station. Then on your upper right is what we call the clarifier. The clarifier or the aerator. Okay. The clarifier is basically what helps you to clean water in a water treatment system. Let me give us one secret about water treatment. Very simple secret. Treatment of water is simply oxidation reaction. When you bring water from a borehole or from a dirty water, for instance, what that water is lacking is basically oxygen. It has oxygen deficient. It is oxygen deficient. So your job is to the minimum oxygen requirement in a clean water is about 8 milligram per milliliter, per liter, sorry. So the BOD of wastewater is between 300 and 400. When we say BOD, the biological oxygen demand, what that means is that this is the amount of oxygen you need to be able to clean it. In other words, you need about 300 to 400 grams of milligrams of oxygen to be clean. That's what it means. I'll not say much about that because I'm not doing wastewater treatment. Then on your right is a filtration bed. What you have here are something like a trough. This is how water, water, when you want to do a simple filtration system, you pass the water through a filter bed or filter membrane. That filter membrane is made up of sand material, and it can also be made up of other material that is in the form of fine grains. And so there's always the way you distribute it. You start with what we call the rapid sand filters, then you go to the medium sand filters, and then you go to the low sand filter, depending whether the water is moving in line with gravity or against gravity. Okay, my colleague just explained this. In every centralized water supply systems, these are the basic components. The first component is the collection system. So you have to design the collection system, which is a water source, okay, the raw water source and the treatment. The second system is what we call the transport system. What we call is the transport system. Then the third is the treatment. So this is the treatment system. And then the last is the storage. Okay. And then after the storage, you now distribute. So what he was trying to say again is that for all the components on my right, you design them based on hourly flow, which is the distribution system. While the component on my left, which is the transport, the treatment, the collection, you size them based on daily flow. So in a wastewater treatment plant, they will tell you the capacity of the wastewater treatment plant is so per day. Per day, everything is per day. But when you come to the distribution network, it becomes per hour, milliliter per hour. The water demand at every node should be so liters per second. So that becomes your hourly distribution. Okay. Then the other thing is, he also mentioned this when he said the water demand is about 130 liters per second. Some of you will be wondering, how did you come about this 130? Well, this is an idea of how to derive the 130. It's not inexhaustive, but you all know that every human being drinks about 3 to 10 liters of water per day. For drinking, preparing food, washing up dishes, body care, washing of clothes, and water, and all the household activity, you need between 15 to 25 liters. Then to flush your toilets, to take your shower, to irrigate your garden, to your swimming pool, to wash your car, you need about 40 to 60 liters. Then other things which are external also have their water requirements. So at the end of the day, we have observed, and many countries all over the world have understood, that between 100 and 150 is enough for one single soul per day. Any question or any different opinion on that? That the average human being needs about 100 to 150 liters. Meanwhile, Abuja was designed with 100, by the way. Abuja was designed with 100 liters per capita per day. So we expect everybody living in Abuja not to consume more than 100 liters per person. And the WHO standard says 150. Okay, Mr. Roberts, can you say something?
Yes, a quick question comes to my mind. Nigeria, is there a Nigerian standard for how much liter per person and day? Like a network, we need to design a network in Nigeria specifically for Nigeria, or is it something on federal level or state level, or where can I find the standards?
Thank you very much. This is a very good question, Robert. Robert, sometimes I feel ashamed to answer this question because we've not been able to regularize our water standard. But so far, the Federal Ministry of Water Resources They are small-scale term projects. They have developed some standards, but the standard is still part of the National Water Resource Master Plan that is currently before the National Assembly. It is yet to be adopted. It is yet to be implemented. It has been a controversial thing, but so far what they did was to have about 3 tiers. At the urban level, they said 100 in the document I have cited. For the rural areas, they say 60. Then for the semi-urban is 60. Then for the rural areas, they said it is about 30. But so far, we normally use the design for Abuja as a reference. And what we do, what most of our engineers do these days, is that we adopt British standards, which I know is something close to the Euro code and the German standard. The German standard in most cities in Germany now is about 120. Based on the ATV 118A, I think it's about 130, 120, 130. Yes. Then worst case scenario, you adopt the WHO standard, which is 150. But for now, our reference standard is 100. And I'm very careful to use the word referenced because it has not been adopted, adapted, and authenticated. Thank you. I don't know if that answers your question.
Yes, very much.
It's a tricky one, I must say.
Thank you very much.
All right, sir. Okay. So now, this is just to give you, to justify why we need a clean water. It's not necessary. It's something that happened in Germany many years ago. As soon as they adopted, more than 40 years ago, as soon as they adopted a good water supply system in some cities in Germany, they found out that the death rates went very low. So this is not too important for now. But the idea is that, and I always tell people, if you can take care of what you drink, you will reduce disease infection by 40%. Quote me anywhere. If you can take care of the water you drink, you will minimize your going to hospital by 40%. Just what you drink. So take note of that. So when after this is a take home for us, make sure you always go for good quality drinking water. Okay. So still on water, there are many constituents in water. I've said this before. You have the chemical constituents, you have the microbial constituents. Impurities can come in different ways. And the impurities can also come into your water through the source, through your treatment. You can use some chlorine compounds and it can affect your water, which has been banned now because of carcinogenic effect. Then during transmission and storage, you can also have impurities in water. I know what they do in somewhere in US, in California. They transmit their water from Mexico, Gulf of Mexico, somewhere down into California because California is a very water-stressed city in the US. So they convey their water through something like a conveyor, open trapezoidal membrane, just to minimize losses due to evapotranspiration. Then when it gets to a point of use, they now start to treat it. So you can also treat at source, or you can also treat at point of distribution. Okay, so water has some basic requirements. We say that water must be free from every pathogenic organisms. That is a standard. Then no compound with negative effect on human health should be found in water. It must be clear, it must not be salty, it must not have a bad taste, and it must not be smelling, it must not have bad odor. And then finally, it must not be corrosive or to encrustate the water supply systems. So these are some of the things we need to talk about in how your water has to be healthy. When you are designing a water supply system, you are supposed to have a goal. What is your goal? What is your aim? What do you aim for? Is it to supply water? Is it to improve on existing water? Is it to clean the water? So you should be able to define. So normally the general definition or the general goal of a centralized water supply system is to supply all consumers around the clock with the highest quality, suitable quantity and pressure, low cost, and minimize impact on natural water cycle. So this is very important. It's a philosophy. As a water expert, as a consultant, when you are choosing your water source, when you are designing your water system, you must have at the back of your mind that highest quality is your baseline. That quantity must not be compromised. And while not compromising quantity, you must make sure that the water is sustainable. In other words, if you are using groundwater, you must be able to know the recharge of the aquifer. You must do your pump testing. You must be able to test your aquifer and make sure that the recharge rate is more than the extraction rate. Then the next thing you need to consider is to know that you need to extract this water at low cost. You must make advantage of low cost. You must make sure that it doesn't make a point for you to supply water at such an exorbitant cost that it will be within the out of range of the average consumer. Then finally, there should be a minimum pressure which you have really dealt with in this course that's required in your network. So if you're able to meet this demand, then we expect your water to be hygienic, to be safe supply, to be comfortable, to be economical, to lead to social economic development, and to maintain natural ecology. Biodiversity must not be compromised. So these are just some statistics and data about the water cycle. These are just some examples you have about water. So this is the end of chapter 1. So I'll go to chapter 2. Some of them are not as lengthy as this. So I know I can meet up with my 1 hour goal and target. Okay, the next one is your water collection. Water can come as long distance water supply. It can come as surface water. It can come as surface water. It can come as groundwater. Underground water, it can either come as recharge water or it will come as natural groundwater. So irrespective of how it comes, there are different treatment ways you can conduct. Like for instance, for the surface water, it can come as a rainwater. It can come as treated sewage. Somewhere in Namibia, somewhere in some African countries, they've been treating their wastewater and they recycle into the system. It can come as seawater. It can also come as river water. It can come as lake water, like we have in Germany. In the southern part of Germany, they have the Lake Constance, which is a very important water for them. Then you have, they can also come in form of a barrage. Then the other one is your intake structure. Your intake structure. Okay, somebody said my expectation is to be able to model water quality using the Epanet. Okay, that's from Lucy. Water quality. Lucy, well, let's talk about the quantity. Then we'll see how we'll look into the quality also. Okay, then the next one is after then the water will go after the intake structure, it goes to the treatment. And after the treatment, it goes to distribution and storage. And for some, if the water is coming from long distance water supply, like a water board or central city supply, it doesn't need any other treatment because treatment has already taken place. So all the water needs to do is to just go to distribution and storage. Then, if you are choosing a water source, you must consider quality, quantity, economics, and the safeguard of your supply. What do you mean by safeguard? Your water should not be located where there should be contaminants. You shouldn't locate your water close to a landfill, a septic tank, a treatment plant, or an agricultural estate or agricultural plantation, because surface runoff from fertilizers, NPKs, will introduce nitrates into your water. So you must make sure that your water, the location of your water source must be free and must be able to meet up with these requirements. And in choosing your water source, we prefer spring water. Spring water is the best. The second one is groundwater. The third one is surface water. And in surface water, there are two of them, the lake and the river. We prefer the lake water. Then you have the rainwater harvesting. You have the long distance water supply. Can somebody in a very short, can anyone tell me why spring water, the difference between spring water and groundwater? Well, let me not take time. The spring water, the difference is that the spring water is like an artisan well. The spring water and groundwater are the same. But for the groundwater, you need energy to pump it. Whereas the spring, is already under pressure, so the water is coming out. The pressure of the water is at the surface, so the water is just coming out. I know that in the western part of this country, we have a lot of spring water there because of the mangrove and some other some volcanic activity that took place many years ago. So there are just these features and fractures in some of the aquifers there. Okay, the next slide will talk about groundwater. We all know groundwater. These are the properties of groundwater, the hydraulic layer, the porosity, and what have you. We talk about the parameters. So all these other ones, when you read them, you're definitely going to understand them. So I'm not going to waste my time. I'm not going to waste our time, sorry, going through this, because I know that if you go through them, you're going to understand them because they are self-explanatory. So let me go into those ones that I know that are a bit technical. I'm sorry, I know I'm very fast, but bear with me because we have 3 days to do justice to this course, and I'm trying to make sure we touch every area so that we can have we'll be able to cover as much as possible. So full screen mode, thank you. So we've talked about this. I think we'll read this, we'll understand it. We're going to understand this. I've said this before. Consumer groups of water, types of water demand. Now, water demand, like we say 130. 130 is just for household demand. When you talk about, it's just for domestic demand. Okay. Agriculture have their own demand, like livestock for irrigation. Crop water demand. Every crop has its own water demand. Rice has its water demand. Annual crops have their water demand. Mangoes, orchards, they all have their water demand. Then industry demand is also different based on what you're producing. Tanning industry, milk industry, brewing industry, every demand. So there's a water demand you need to be able to perform those industrial activities. Then you have public demand. Public demands are those demands for administrative buildings, for schools, for hospitals, for gardens. Then you have your own needs of water. Then finally, you have firefighting demand. So here is just discussing about, based on the distance of water location to the consumer, there's a reduction, there's an influence on reduction of the water demand. So it's a function of how far you are. So you can agree with me that if you are the further you are from water source, the less water you consume. So this figure just shows us how that can be influenced. Okay, this is what my colleague mentioned about demand pattern. So if you look at this is a demand pattern for winter and summer in northern and southern part of Germany. You can see that in the summer months, okay, in the January, in the first few months, in days, sorry, you find that the water demand is a little bit low. Then at the summertime, when people take a lot of baths, people use a lot of water, the demand tends to be higher. This is not important. Then the next one is your consumption characteristics. Okay, you can see that in a 24 hours day, the consumption varies. For rural areas, for small towns, for big towns, there are different consumption patterns. Okay, for the small town, for the rural town, you can see that between the hour of 0 and 5 o'clock in the morning, most people are like sleeping. Immediately it's 5 o'clock, the demand jumps up. And then around 8 o'clock, 9 o'clock, it goes down. Then in the afternoon, when they are coming back from farm, in quotes, you see the demand goes up again. And then towards afternoon, it goes down again. And then at night, when they are ready for cooking, everybody's home. They want to take their night shower. They want to cook the evening meal. The demand goes up again and then goes down again. Then for the green line, the same thing. It has about 2 peaks, which is mostly in the afternoon. Then for the big town, the demand simply, the peak are not much, but they sustain themselves for almost a period of 12 hours before they now go down. Okay, we talk about water forecasting. It's a forecast of water consumption expected at an exactly defined area of supply within certain design period. Now, if you are doing water demand calculation, if you are designing for a 50-year planning zone, then it means you use the population of 50 years. So if I'm designing for water for the next 50 years, I'll do my population projection and say, what will the population be in 50 years' time? That will be the value I will use. Does anyone have a problem with that? Assuming in a 3-bedroom duplex, a 3-bedroom flat now, we're expecting 5 to 6 people. But in 50 years' time, we're going to expect 10 people. It means you're going to use the value of 10 to do your calculation and your design. And also, you need to forecast the development of the different consumer group and their consumption behavior. And what is the goal of all this? To be able to determine the most current design peak flow. I love that word, peak flow. Peak flow, you need to design the highest amount of flow they need, the highest possible amount that is needed. That is what you're going to define for. Engineer John Aboifo, are you here? Engineer John Aboifo. Can you unmute yourself? Can you chat me up, please? Okay. So let's continue then. Okay, so detailed analysis of supply area, measurement of current states, forecast development, and all these are some of the things that we need to do in your forecast. So you must take care of all these forecasting parameters. Then here you also look at the average. You can talk about the consumption characteristics of household and small businesses in terms of their yearly and their maximum. So if you have what we call the average specific daily demand, which is said is about between 100 and 150, then when you multiply it by the safety factor, it becomes the maximum specific daily demand. And that is what you use for your design. So we have two factors of safety. We have the daily peak factor and the maximum hourly peak factor. So these are the two factors. When you are designing for the tank, transmission network, treatment plant, you use the daily. When we are talking about the distribution network, you use the hourly. So for the hourly, you're supposed to use the hourly peak flow also. Then coming down here, this is also how you generate your demand, your peak flow. But the formula is here, so you can use the formula and then put it, and then it will generate a table like this. So these are the peak flow you can use based on the number of inhabitants you are designing for. And to use the formula, if you know the formula, you can put the formula down here, and it will give you the hourly peak flow. So let's assume like in Abuja. Abuja was designed for 1 million population equivalent in 1978 when the design started, and in the early 80s they finished it. So they used about, here it says you use about between 1.77 and 1.38. What this thing means is that after getting my demand, I'll multiply it by this factor so that it will give me the peak demand. Those of all of us are engineers. You remember when you, after doing your design, you multiply by a peak factor, you multiply by a coefficient. Why do you do that? That coefficient is to take care of any design faults or anything that you didn't capture in the course of your design. So that is what P factors does. And P factor helps to give you the worst case scenario. So after doing, some of us, after doing your cost analysis, we normally multiply by 20% or 1.2. Some of us multiply by 1.1. Okay, so multiplying by this will help to give you the maximum peak flow. So this table gives you an idea of the water demand of the different sectors, whether it's the hospital, the schools, the administrative buildings, the hotels, agri, commercial, and what have you. Where I want us to pay attention to is the administration. If you look at the calculation, it's about 25 liters per employee per day. Does anyone know why it is so low? Or for schools, look at schools. Schools is about 6 liters per parent teacher per day. The reason is that in schools, they don't shower, they don't cook, they don't wash cars. All they do is to drink water and then maybe wash hands for toilet. So we assume that 6 liters is enough for that. And for administrative buildings like secretariat, we assume 25 liters. Why? Because nobody lives there. After 4 o'clock or 5 o'clock, everybody goes home. So between the hour of 10 or 9 o'clock and 4 o'clock, we expect you not to consume more than 25 liters of water. And I think it makes sense. Okay. So this is just what my colleague explained. For a population projection, Pn equals to Po. Okay, if you open the bracket, it becomes Po plus N in percentage raised to power number of years. So if you use this formula, you will get if you know the growth rate, Nigeria is growing about 4% per annum. So if you use that, it will enable you to know the population projection in a certain number of years, after a certain number of years. And how different types of population growth, these are the formulas. You can apply any of the formulas. There are many formulas out there. You can choose any one of your choice. Then this is not necessary. Okay, so that's the end. Any question? Chapter 4. So chapter 4 is giving us example.
Hello, sir.
Yeah, I can hear you, sir.
Someone just type on the chat, on the group chat. Can you just look at it?
Respond. Okay. Why do you not consider tertiary institutions? We mustn't specify. School is school. I don't know. School is school. I think for tertiary institution, we should use the administration for the up-school area. Then for the residential areas, for their hostels, you should use the domestics. You should use the domestic. Then for lecture halls, you should use the one for school. Are you okay with that?
Sorry, what about the religious organization?
Churches. Churches, you use the value for school. Because what we do in churches is either we wash our hands or use the toilets or drink water. So 6 to 10 liters is enough per person. Okay. Except for religious bodies where people are inhabiting there. Or if it's where people come and go. In fact, on a work days, you should even consider, though you use the peak factor design, and that peak factor is service days. Service days, the days their church will hold. That's the day you use for your design. Yeah, that's a good question. It shows you're following, and I'm impressed. Okay. So now, we've talked about these 3. So these ones will really understand how do you select a water supply system. You have to take into account who is responsible for the water supply system, what is the economic situation of the people to be supplied. You must not supply water that they can't afford. Then what are the local situation? What are the local situation? Do they have river? Do they have groundwater? What is the recharge? And so on and so forth. Then what's the availability of the water resources? And then how do you safeguard? How do you build a buffer so that people will not go and you don't go and site a water system close to their sanitary system and all that. So grade of water. You read these ones, you understand them. It's self-explanatory. Groundwater. Examples. This is an example of a gravity system and a pump system. 99% or 95% of water supply systems are through gravity and gravity systems. Only few cases that you have a pump system due to space or lack of innovation. So this is an example of a community water supply system. Here in a city, you see that the city is made up of 14 communities, and that is a total of 120,000 inhabitants. They have about 14 wells. 14 communities, 14 wells. That means every community has one well. Then they have 4 treatment plants. Then they have 35 storage tanks, meaning an average of 2 per community. And then they have 1 water tower and 200 kilometers of transmission pipe and other local resources. Another example is in certain part of Germany called Baden-Württemberg. Here, it is made up of 320 communities with an equivalent of 4 million inhabitants. The flow, the daily demand is about 360 meters cubed per day. But the maximum specific demand, in other words, after multiplying by safety factor, is about 531 meter cube per day, 531 meter cube per day. So this difference between this one and this one is that you have multiplied the safety factor into this one to take care of any population explosion, any changes in demographics, any changes in calculation, anything that can come up will be taken care of. And the water source is 1 treatment plant, and they're using 1 treatment plant and 1 lake, and they have about 29 storage tanks. Okay, and they have 1 resource, which is lakes constant. This is another one for California. I mentioned it, okay, and so on and so forth. Okay, we're on track. We're in chapter 4, we're in chapter 5 now. Okay. So in any design work, there's always a primary design and a final design. And that's by the way, health risk, I've talked about it. Minimizing environmental impact, you have to choose the water source and take note of the location of the water source. Okay, so here you have minimum cost, which is minimize length of pipe if you want to have a minimum cost, minimize number of pressure zones, minimize your treatment, and minimize your pumping. So minimize, minimize, minimize. And that's all. When we read all these things, we're going to understand them. Zoning, we talk about zoning. Okay, say analyzing topography and boundary of condition area per zone. So you have to zone them. Choice of point. I think we'll read all this, we'll understand them. This is end of chapter 5. We'll go to chapter 6. We're on track. Okay. We've talked about this. We've talked about pump system and the gravity system. Okay, this chapter 6 is talking about types of pumps. Okay. Why this is important is that as a water expert, you're supposed to be an all-rounder. You're supposed to know not just how to design, but also the component of the system. So this is a centrifugal pump. Centrifugal pump has a pressure pipe, it has a channel or casing, it has an impeller, it has casting, it has a suction pipe. Okay, these are different types of the centrifugal pump. You have the single stage and you have the multiple stage centrifugal pump. You have the submersible pump, you have the vertical shaft, you have the horizontal shaft. Then the speed of pump is rated in revolution per minute. The higher the resolution, the better. And suction pump has a maximum head of 6 to 7 meters high. And pumping station, we must have at least 2 pumps and so forth. Just read this to understand them. And this is an example of a power booster and the hydraulics. Sorry. So these are typical arrangements of a booster station. And when you're looking for head is made up of 3 components. Number 1 is geodetic head. The geodetic head is just the difference between the upper level of water and the level of the consumer, or level of the tap. Then the head loss due to velocity is that when water is flowing in a pipe, it's losing head due to its activity within itself and together with the choice of the material. Then the frictional factor 2 is another type of loss. So there are basically 3 losses that you need to, and these losses are computed in form of loss in meter head. In other words, if I'm to buy a pump that will overcome 20 meter head, because of losses in my system, I might not buy the one that can overcome 25 meters. So I can take 5 meters. Then the next one is okay. Okay, good. So we've also discussed this. If you want to understand the hydraulics of a pumping, it's simply a function of the head and the discharge. The other things you see there are all constants. This 1,000 naira is to convert it to watt to kilowatts. This N here is the efficiency. This Q here is the flow. And this is acceleration due to gravity. So once you have the flow of a stream, of a river, and you're asked to know the hydropower potential, it is easy. Once you know the discharge of a tank, you can say when that tank will discharge. Pump curve, we talk about pump curve, pump in parallel and pump in series. We want to say what they mean. When they are in parallel, when a parallel connection, it means that the head will remain constant, but the quantity will increase. In other words, you have 2 pumps pumping water out at the same time, at the same period. Whereas if they are connected in series, in other words, they are connected together, then the water will be so massive that they are running into trouble. Okay. So we will all do this, understand this. Okay, this is the end of chapter 6. So we'll go to chapter 7. Any questions so far? We have less than 15 minutes or less than 20 minutes because we started 10 minutes late also today. So my colleague have already touched on some of those things. What I'm just doing is to show you where they are, and then so that when you are going through them, you will be grasping everything about them. Okay, so function of elevated strength tank, we say is to equalize the difference between the inflow and actual demand in the system. That is the function of elevated tank. Number 2 is to provide water and pressure in case of breakdown in the flow. So if not that there might be a case of breakdown in the flow, then sometimes we might not even need a tank. The next one is to provide hourly constant pressure in the network. Sometimes your elevated storage tank is also to bring about a constant pressure because the tank is fixed. So the difference in elevation between the water level in the tank and the tap level will give you the pressure difference. If it's 20 meters, you know it's two bars. If it's 10 meter difference, you know you're operating within 1 bar, and so on and so forth. Okay, then there are types of elevated tank. I've said this before: storage, surface storage, water, and the rest of it. Okay, so what level, like my colleague have explained this, I don't think I need to go through this again. My colleague have said it all. If you want to determine the level of your tank, the formula is that you have to add the service pressure plus the losses. service pressure plus losses will give you your tank. Sometimes we ignore losses. That was why the one we did for the houses that are located at 240, the minimum position of tank will now be 260 because we're adding 20. Whereas those houses that are at elevation of 180, 185, we're now adding them 35 plus 20. That will be the maximum. So this is just what my colleague explained. But just know that the maximum service pressure in the network is less than, it must be less than 80 cubic meters of water, which is 880, which is 8 bar, sorry. So what you also do here, you can see that the first floor is 20, second floor is 25, third floor is 30. So if it's giving me a 3-floor building, I'll know that the service pressure I'm expecting there should not be less than 30. So for your zoning, like he said, if you want to understand how you zone your network, it will be maximum service pressure minus the minimum minus the height of tank or height of water in the tank, then minus acceleration due to gravity. Okay, so these are the definition. This is how you go about them. So he has explained this today to get your. I don't know whether it's Shitu that asked that question, and let me tell you that is the wrong way. I don't know whether somebody mentioned that thing, that you use the daily demand of your people to size your tank. If you do that, you'll be correct, but the size of your tank could be so big, so massive. In Abuja today, the Abuja network, they pump water every 30 minutes, every 1 hour, because the tank we are so small that it can hardly retain water. So this is the exact way to understand the volume of a tank. You talk about the equalizing volume, you talk about the emergency volume. Meanwhile, emergency volume is usually 20% of your water demand. So in other words, after getting your equalizing volume, you now out of the total volume of water you need or the water demand of the area, you take 20% of it as your equalizing volume. Then you now take the volume for water firefighting, which is for 2 hours, 1 hour firefighting. You take it and put it together. That becomes the size of your storage tank needed.
Hello.
Yes, sir.
Can I ask a question? I think this the sizing of the overhead tank, to me, I think is a trade-off between owning cost and operating cost. I don't think we can limit it to just that because you don't want to save money and you can size your tank based on the equalization volume. What that means is that the client is going to pay more for operations because you'll be pumping. True. And so power of the pump will be consuming power. So it's a trade-off that you need to decide on which one pays you more.
I love that. Yeah, I agree with you. I agree with you completely. You need to balance it against other factors. Yes. Yeah. Okay, that's good. And also, you need to know how many times we need to pump in a day. Is it once, twice, or 3 times? I'm talking about you saving energy now. So when you do that, remember, if you need 1 pump, you must provide 2. If you need 2 pumps, you must provide 3. There must be 1 off, 1 on. Is a rule. You must provide 1 extra pump. So that in case of breakdown or maintenance. Okay, Robert. Robert has a question.
Yes, please. You say the volume for firefighting, it says between 48 and 384 cubic meter. I mean, that's a huge range. So where do I get the information of how much should I put or add for firefighting? By what does it depends on? And again, please, maybe in the Nigerian context, where can I where could I find like the way of how much should I forecast for this? Thanks.
Okay. Thank you so much. Other hands are raised. You're going to ask a question. The firefighting is depending on how many hours you want to fight the fire. It depends on how many hours. There is 2 hours, there's 3 hours, there's 4 hours. Okay. The minimum here is 2 hours, and that is for 48. So it depends on the hour, but I know others have other opinion. So the major deciding factor is how long do you want to sustain the fire before people from water board, people from the fire station comes. So I know we do the same thing in a reinforcement, in a design, in concrete design. If you are doing cover for reinforcement, you do for either 2 hours, 3 hours, or 4 hours, so that how many hours can this concrete or the structure sustain itself against fire before help, external help comes. So for tomorrow, there's a material I downloaded that gives you an idea, and Robert, I'll try and share that material with you. I think it's in our folder already. It's part of it. I think check your folder. There's a material from a US standard that I picked up. And I'm sorry, Robert, when you keep asking me about a Nigerian standard, we don't have much of a standard. We are using British standard, and we are working on it. Okay. On that question, who else want to ask a question?
Yeah, I want to ask. Hello, sir.
I can hear you, sir.
Yeah. For the firefighting, I've heard what you said. I want to ask, maybe we've been teaching wrong things from everything we've read. We normally is supposed to be a percent built into the total demand. When the hydrants are spaced along the streets, that firefighting is built into the total demand. Is a
percentage.
Yes, that is what many years ago when we graduated we were taught.
Okay.
So that is the wrong approach, because that's what
it's like a 20%.
20.
Yes.
Okay. Yeah, so let's say 20%. Okay.
20%. Yeah.
Okay.
And 20%, between 15 and 20%.
Okay. I agree also. But some countries, they define it based on the design hour, like I said. It has to also do with location of the nearest fire station. If you take them 1 hour to arrive, maybe you design for 2 hours. If you take them 2 hours, you might design for 3 hours. And also, other countries can say 25% or based on range. Someone says between 15 and 20. So I agree with you. I've not really thought of it that way, but there's truth in it. It definitely makes sense, because it's a percentage of the total.
Yes.
So it means 20% of this volume is reserved for firefighting. There's sense in it. Okay. Any other hand raised? Okay. No other hand.
Hello.
Okay, go ahead.
Yeah. In determining the fire water, what we normally do is based on the standard you are designing to, whether normally you can design to NFPA or design to BS standard.
Okay.
It's also dependent on the type of firefighting system you want to design for. Whether sprinkler, if you are designing for sprinkler, they are recommended minimum hours of pressure. You have to fight the sprinkler has to work, whether ordinary hazard or high hazard or light hazard. So they are recommended by standard that this is the minimum amount of time that your system has to work, and we have to multiply that with the flow. Also for the hydrant, also they have recommended hours of storage. That if you're using hydrant system, you have to have a minimum storage of 1 hour to fight the fire. So it depends on the code you are adopting for your design. Exactly.
I agree with you. I think you just repeated what I said, that despite the percentage factor, one thing I want to tell designers is that after your design, you have to justify your parameters you use, and justifying them could be in a form of referencing the code, the standard you use, and the justification for them. So I agree with you. You've talked about 1 hour design, 2 hours, and that collaborates what I just said. And by the time you do your calculation, you could find out that 20% of the total volume might also fall within that range. Thank you. Any other question, please?
It's just a comment. I think anything that is not backed by code or standard should be avoided. I don't think you see in any code or standard where they will tell you to size fire water based on a percentage. Better you follow the right standard. And as Mr. Waza said, if you want to now try to determine what is their percentage, you can do that on your own. But if that is not supported by any standard or code, I think we should avoid it.
I also agree with you. I also agree with you. As if it is not backed by any particular standard or code, it shouldn't be the case, because we need to be guided by some framework, sort of. Okay. We have like 10 minutes. I don't know. This is chapter 7. Any question? I think I've thought about this. We've taught this. We spoke, my colleague emphasized this at length, and Robert was asking how to read it. Well, if I'm to read this at 8 hours, the first 8 hours, 8 a.m. in the morning, the flow is 66 cubic meter of water, while the consumption is about 30. Okay. At this hour, it is this, and then the difference will give me that quantity that I need to save in a storage tank. If not, that quantity will be wasting. So what this thing simply means that at this point, people are just waking up in the morning, water consumption is low, but there's a lot of water which is going to waste because we're pumping all through the day. And here we're pumping for while people are sleeping, which is at night. Which is at night. Okay, so here you see that the biggest difference is between 30 and 200. So that gives you 170 as your equalizing volume. This is the equalizing volume we're talking about. So you now add 20% of this, add your firefighting to get your total volume. Okay, but if you do water demand, which I'm going to show, I also tell people to do that as a guide. When you do your total water demand, convert it to daily factor. You can use it as an idea to say this is the maximum tank size I can use. In other words, if I'm going to pump once a day and store water for 24 hours, this is the maximum tank size. But that tank can be so massive that you need to break it and say, I'm pumping twice, once, thrice, or 4 times a day.
Most regions pump 4 times a day.
Thank you. I agree with 4 times a day. It depends on the size of the district anyway, the size of the habitat, the population equivalent. Okay. If it is too high, you might pump more than 4 times. I say in Abuja they pump up to 10 times a day or 12 times.
In Calabar, it's 4 times.
Okay. In Abuja, they pump up because they have only, Abuja is supposed to have about 10 tanks, but so far we've only built 4. Okay. Only 4 tanks.
That's where the problem is. 2
are under construction, and government money is gone, money is finished.
Okay.
So we have only 4 tanks. So, and you have population explosion. In fact, yes, only 1 tank is serving Guarempa, and it doesn't do just a small portion of Guarempa. Then 1 tank is serving Wuse, the other tank is serving Gariki. The tank that's supposed to serve Gudu, they are still working on it. In fact, they just awarded the contract for the design. Before they have money issue. Then Apo, the tank in Apo is still being built. Many tanks. I've seen the distribution of Abuja. It's beautiful, but it's work in progress. I don't know how it is in Lagos.
With that kind of population.
You're only in Lagos.
Abi.
Okay. You understand? Big mega city people. Is that going to be a mega city?
We are watching.
No. That's not a mega city. Well.
Okay. They started with having municipal water, but it wasn't sustainable. So now, OYO for you.
Abi.
well, the way to start it, I think the new district, there are those Epe axis. Is it Epe? Yeah. Epe Aja axis. They could do something. They could start there because Rome was not built in a day. They could start.
Like somebody said, that municipal arrangement will be the best.
It's the best, but when you don't have a control, you don't control population, you end up having people downstream who will not get water. But I believe there are still people who have water. Tomorrow we'll get to know about this thing. Why in a estate, those downstream don't see water. Those upstream will see water. You also got to understand why someone living at the fourth floor of a four-story building doesn't see water at the peak period, whereas somebody at the down floor will be getting water. It happens a lot of times.
Yeah.
It happens in most of our universities, because when they designed this thing, they didn't anticipate, they didn't factor what the service pressure. As you are going up, you're increasing it.
Yes.
But if you now use 20 to design everybody, and you now go and build 6-story building, 60-story building, the service pressure should be 20 plus 5 plus 5 plus 5 plus 5, which is about 50. So service pressure for a 5-story, 60-story building should be 50 cubic meters of water, or 5 bars. So if you now go and use 2 bars to do it, that means when you get to 5th floor or 4th floor, water will cease, especially during the peak period, thereby making the person uppermost not to see water. Okay, that's by the way. Well, we are closing the class in the next 5-10 minutes, please. Then look at also what my friend was trying to explain to you. If the pressure is so high, you break them into pressure zones. So you can see we have the tower zone, upper zone, lower zone. So you can see that you break the pressure so that the pressure will not be more than 8 bars. So you can see that here, from water, the storage tank will supply to this tank. Then water from here cannot get to the person here. It will come under too much pressure. So what they did here was that the water here will first get to this person, then from this person, it gets to this person. So that the water, the service pressure will maintain within a certain range. So the next thing here is a surface tank, how to plant surface tank. It can be elevated tank, it can be surface tank, it can be underground tank. It depends. It can have a riser inside, it can have a washing mechanism inside, it can have a different, can design it like a house. I mean, there are different shapes, different styles, different systems. It can also be equipped like a sophisticated machine. Okay, so this is a tower. We don't have any. I don't think we have any water tower in Nigeria. In Dubai and Middle East, they have it a lot. Okay, these are the ones they have in Middle East. Okay, chapter 7. So the last is chapter 8. So sorry, we have overshoot our time, but remember we had a small grace period starting the class. So chapter 8, what I will say is that chapter 8 and chapter 9, let me see what is in chapter 9. Oh, there's no, okay, chapter 9. Let me do chapter 9, then I'll come back. Let me make sure I have only one chapter left. Okay. I'm on chapter 9. I'm doing chapter 9 now, but I'll come back to chapter 8. I didn't want chapter 8 is very sensitive. But let me make sure I've done with chapter 8. So chapter 9 is this. Chapter 9 is something we can read and understand. Your distribution can be either by gravity or by pump. Then transmission can be using different methods. Types of distribution. You have the branch system, you have the loop system. Okay. Pressure pipe below ground level can come in 2 forms. Can be a branch system, can be a loop system. And you can be looking at this, and it's self-explanatory. This is a branch system, what it looks like. And this is a loop system, what it looks like. And we'll talk about service pressure. This is service pressure. Remember this service pressure. This is like reminding you to remember it. Then these are materials. Okay, these are their lifespan. These are their maximum pressure they can take. And these are their corrosion resistance. So like steel now, we have line and online steel. The cost is very high. The corrosion, we have the line one is good, the online one is bad. The maximum diameter you can anticipate is about 2 meters for steel pipe. Okay, you can take up to 110 bars. Okay, no, it can take up to 100 bars. Sorry, steel pipe can take up to 100 bars, which is 1,000 cubic meters of water. Okay, and it can last up to 40 years. Ductile iron, the cost is high. The line one is good. Online one is medium against corrosion, medium resistance against corrosion. The diameter, you can get more than 1 meter. The pressure must be less than 25 bars for ductile iron, and it can last for 100 years. Asbestos cement, we no longer use it because they say it's carcinogenic. It can cause cancer. It can last up to 30 years. It can only take less than 100 bars. It cannot be more than 1 meter in diameter. It is very good against resistance. Then you have the plastic PVC pipes. PVC pipes will last for 25 years. They cannot take more than 10 bars. Things have changed. There are PVC that can last for 50 years now, I must say. And there are some that can take more than 10 bars. But you must limit yourself to what's available in the market and what is commonly available. Okay, and PVC normally take less than 300 mm, 1 foot. All of us know that things have changed. These days you can get 600 PVC pipe. Then against resistance, they are very good. Against cost, they are very low cost. So these are the things in chapter 9. Please read and understand the other ones. The other ones, my friend have explained this energy line and pressure line. The difference between energy line and pressure line. Every water has 3 energies: potential energy, kinetic energy, and energy geodetic height. Okay, it's here in the next slide. Look at Bernoulli equation. Bernoulli says that the head loss, or the head that should be overcome in a system is there's a velocity component, there's a head component, and there's a height component. 3. And so on and so forth. So here, if you just go through, you'll understand. They are very self-explanatory. So roughness of pipes, I have explained it. Every pipe has a roughness. If you Google them, you have them. Just Google, say pipe roughness. If you're using PVC pipe, there's a roughness. If you're using ductile iron, there's a roughness. So this roughness is also telling you, depending on whether you're using the pipe for transmission, there's a certain roughness that's expected. If you're using it for main distribution, there's a certain roughness that's expected. If you're using it for secondary pipe in your display network, there's also a certain roughness that's expected of you. These are just to guide you, and so on and so forth. Here you can see economic diameter. What this table is telling you is that if you know your flow, your velocity, and you know your flow, you can easily determine your pipe size. In engineering, we have what we call economic design. Economic design means I don't want to give myself headache. I want to design based on minimum consideration. So here you use this. So if you don't want to bother yourself with my charts, with my table and everything, with my graph, you can just come here and say, if my flow is 70 liters per second, I'll use a 300 mm pipe. And the velocity at that point will be 1 meter per second. Tomorrow you get to see how all these things are gotten. You see how all these things are gotten. But these are economic diameter. These are just things that will give you a quick design without passing through the rigor of doing your design. If you are dimensioning your pipe, pressure pipes, these are some of the things you take into consideration. You calculate your head loss, calculate your slope, make your choice of roughness, then you determine your diameter as a function of your slope, your roughness, and your discharge using the nomogram or tables. Okay, one of the assignments I would like to give to some of us, especially those of us that are working in consultancy company, is to go to Google and try to Google some tables used by some US agencies for pipe sizing, because I use nomogram, and it's okay. So if you bring them, we can compare the values in them and the values in the nomogram, but I bet you are going to get the same thing. Okay, so all these other ones, when you go through them, I didn't know my camera is off. So if you go through all these ones, you're going to understand every single one of them. Every single one of them, you're going to understand them. They're all well explained here. Then the slope. This is the slope over this. Okay, and our slope, tomorrow you find out that our slope will be per kilometer. We'll be doing our slope based on per kilometer. So after getting our slope, we will convert it to what is that per kilometer? That is the value we use to do our pipe sizing from our charts. It's going to be kilometer based. And so on and so forth. So this is we've talked about this, talked about Bernoulli equation and the gasified groundwater equation. Just take your time and read all these things. Okay, these are the pressure about pipe in parallel and pipe in series. When you put two pumps in series, the head, the flow will increase. When you put them in parallel, the flow will increase, but the head will be the same. When you put them in series, the head will increase. Just take note of that. So that is the end of chapter 9. So chapter 8, I can't go through chapter 8 all through. So let us know that we are starting tomorrow, chapter 8. So chapter 8 is what we're going to start with tomorrow. I have to end the class here. So chapter 8, it is what we usher us into our design. Our design is in folder, workshop files and folder. Let me just open it. So this is what we'll be designing tomorrow as a case study. This is what we're designing. This is it. So this is a layout. It's a small layout because this is a small class, a time-based class. But after you finish this one, you will now be able to do a bigger class. So before we do our class tomorrow, we'll also develop this as a calculation sheet. In my last class in SIWA, those that were in SIWA class, I told us to go online and look for SIWA and STORM rational method templates. If you also go online again and you say template for water distribution network, you're going to see a lot of Excel templates, and you put XLS, *XLS, you will see a lot of templates that will also explain to you, you see a lot of templates. Let me just put it that way. You see a lot